We're continuing on section 4.6. This time we're sketching the graph of r of x equal to x minus natural log of absolute value of x. Domain in here, the only place that is not allowed is x equal to 0, so it's negative infinity to 0 and 0 to infinity. Notice that there's a vertical asymptote at x equal to 0 because that's not part of the domain, and natural log of x shoots toward negative infinities on both sides. And the other thing that you want to see, that's a vertical asymptote, and in horizontal asymptote there is none. Part of it is because it turns out x is much stronger than ln of absolute value of x as the growth toward infinity goes. This is something that we cover in 4.5. So let's take it for granted at this point that x minus natural log of x is actually going to infinities on both sides. And so then the next part is to take the derivative of r of x equal to x minus natural log of absolute value of x is going to be 1 minus 1 over x. If you rewrite it with a common denominator, it would be x minus 1 over x. And we need to do that because we need the roots. Taking the second derivative of this function will end up taking the second derivative is easier if you take the derivative of 1 minus 1 over x, and you end up with 1 over x squared. Now, point of interest are 0, which is not part of the domain, but it still changes the sign, and 1. If I find the sign for r prime of x, anything before 0, remember as x goes to either infinities, then r prime of x goes to positive values. So positive for r prime on the both sides, and the sign changes as we jump over 0, and its sign changes again as we jump over 1. For 1 over x squared, the sign does not change. Just when you pass over x equal to 0, it always stays positive because 1 over x squared is always positive. So the f double prime is always positive. Concavity is always upward. So when I graph this, I have concave up, and one piece is increasing, the other piece is decreasing, and then increasing. And I will have a local minimum at x equal to 1. And this becomes the graph of the function. Now let's do eye-clicker number 2. The function is f of x equal to 2x to the third minus 9x squared plus 7. Which of these number lines correctly describe the behavior of f of x? And so I suggest pausing the video 1 minute and then coming back to it. So now that you paused, what you need to do is, one thing is to find the f prime of x. F prime of x is 6x squared minus 18x, and f double prime of x is going to be 12x minus 18. 12x minus 18. So the roots of the first one, and I can factor this one, I can factor 8 and x, and I'm sorry, 6 and x, and I get x minus 3. So these are the roots factors of the f prime, and here I can factor 6 and I get 2x minus 3. So the roots of f double prime are 3/2. The roots of f prime are x and 3. X and 3. So for f prime, and then the sign changes as we go through it. Remember, f prime is at the 2 endpoints. It's a quadratic polynomial. Endpoints are with a coefficient that is leading coefficient that is positive, so 2 endpoints should be positive. So this one is out because of that. That one's out. And then the sign has to change every time we pass 0 and 3. Passing 0 and 3, here passing 0 and passing 3, 0 and 3, and here 0 and 3, they're all correct. With this one, it's a linear function. It's negative before x equal to 3/2, and it's positive after x. So anything other than that should be, and all three of them match that. So now, what is left? And what is left is that I see that at x equal to 3/2, there's an inflection point because f double prime is changing. So this one that says max is incorrect. That's inflection point. Now, and the other two is that, what do I get? So we said that the sign are okay in here. What I see in here, it goes up and comes down. So this is a max, not min. Here is a max, this one's correct. And I see here it goes down, then comes up. So this should be a min, not max. And this one's correct. So D is the answer.